Hello, everyone, and welcome to the seventh episode of the Wolfram Student Podcast. I'm Sam,
I'm Rashank.
and we're your hosts.
This is the Wolfram Student Podcast, where every fortnight we dive into a new innovative project done by high schoolers using the Wolfram language.
For our seventh episode, let's welcome Hozaifa Bhutta, who will be discussing his project on punctuation being added to a string of text. Hello, Hozaifa.
Hey there. Yeah, my name is Hozaifa Bhutta. I'm a senior at the University Laboratory High School here at Urbana, Illinois, and I went to the 2022 Wolfram Summer Camp for high school students.
Yeah, that's great. So, what other Wolfram programs, if any, have you done, or what other experience do you have with Wolfram? Have you been using it for a while now?
Actually, the summer camp was one of my first major experiences with the Wolfram language. However, I have actually been using it a bit in one of my independent studies I'm doing for school, where we're exploring different physics simulations, exploring different concepts through the Mathematica. So that's been cool.
Yeah, sounds pretty cool. I guess what was it like seeing if camp was your first experience with the Wolfram language? I guess what was it like just to experience all of camp?
Yeah, the camp was a very unique experience, right? I had to wake up at 6 a.m. go because I was in California at the time, so it was the timing was a bit off, but it was nice having to wake up early and being productive in the mornings with our morning activities. Those were always something I look forward to. And yeah, especially the first few days where I learned the bulk of Mathematica that I used for this project, those were uh, really exciting for me because I learned about all these new concepts and I had so many ideas of how to use them into my project.
Yeah, I remember when I was in camp, the worst part was definitely waking up at like the crack of dawn, but I'm glad you enjoyed it.
Yeah.
Right, because you're also in California. That makes sense. But yeah, at least you're able to, do all that while also meeting people from around the globe. I think it's a pretty cool experience.
Yeah, definitely. Meeting people from the different time zones and asking them what times they wake up was always fun to ask.
Cool. And what's your sort of favorite Wolfram function? This is sort of like a fun question we ask people because usually by the time we do these projects, a lot of people have attended camp at least once and they've, explored the Wolfram language at least a decent bit. So are there any sort of functions that you're just like, oh wow, that function is so cool, or just something that stands out to you?
Hmm. Wow, it's a good question. Probably the function I imagine that I use the most um, when working with my project was partition, and that has to do with I guess I'll talk about this more later, but it has to do with how I processed my data. Partition is a very useful function in that sense. I mean, but another one that I also thought was really interesting was net extract for its like ability to extract specific layers from a neural network and just isolate them. And then Wolfram makes it really easy to take different parts of different neural networks and then combine them.
Yeah, I haven't really heard about net extract before, so it'll be interesting to see how it gets used in your project.
Yes, yeah.
So yeah, speaking of your project, let's see what you have for us here. So thanks for sharing a screen. Do you just want to go over sort of the summary of what this does and then start explaining some parts of code that you think are important to understanding the bigger picture?
Oh yeah, of course. So this project tries to automatically punctuate text by using what's called BERT, a bidirectional encoder representation from transformers. The way BERT works is it outputs contextual feature vectors of an input sequence, which are used to capture the meaning of each word in a sequence of text. And then the embeddings outputted by BERT is run through a neural network, which produces a classification of a punctuation type. And this model was trained on a new kind of science, which was written by Stephen Wolfram on a pretty powerful GPU over a 2 hour period. And it reached a relatively high accuracy of 88% on the testing data. So, stepping back, explaining how this works, this is a machine learning driven model, and machine learning is a subfield of AI, which represents the capability of a machine to imitate intelligent human behavior. So that way, ML systems are used to perform complex tasks in a way that's similar to how humans solve problems. So instead of programming the system to prepare for every possible scenario, you give it a sample of real world data for it to train on, kind of like how you would teach a child to learn from real world experiences. The model then extrapolates from their past to make informed decisions in new scenarios. So looking into neural networks, the first one was created in 1944, but they've come a long way since then, because neural nets are essentially a computing algorithm based on how neurons in the human brain work, where they represent a series of complex operations on an input to produce the desired output. And they're made up of a series of rows and layers connected to each other with weights. And by adding more of these nodes, we can actually expand the network and allow it to extract more information from the input. And by training the network is where the ML component comes in. So we can use this network to perform a specific classification tasks, such as like determining whether an image contains a person or not, or in our case, determining whether a word has a punctuation that follows it. And we do this by training the model through a method called gradient descent, which is an optimization algorithm that adjusts the connections in a network by stepping in the opposite direction of the gradient. And the goal behind this training method is to find the minimum of the loss function, where the loss function represents the neural network's inaccuracy on a data set. So this is where the importance of a data set is, because by creating a comprehensive data set and using this gradient descent algorithm, a training method, and tuning the hyperparameters, you can use a network to solve almost any classification problem. So
sorry, it sounds pretty cool. Could you like explain what gradient descent is in like with a metaphor, for example? Because I don't think I fully understood how the algorithm works.
Yeah, so gradient descent is pretty complicated. At first I myself thought of it as a black box. And that's how a lot of people think of it. Does all the magic behind the scenes to adjust these connections between these nodes. It tests the model on training data, and based on that, based on its inaccuracy, it will slightly adjust these connections to decrease the inaccuracy of this, and it does this by trying to find the minimum of a loss function, sort of by actually finding the derivative with respect to the weights on that loss function, and it steps downwards to find the local minimum. Again, it's a bit complicated and hard to explain. I could have definitely put a diagram here showing like a ball rolling down a slope, because that is how people represent it, where the ball represents the algorithm's accuracy right now, and the slope represents how it's slowly the inaccuracy is going lower and lower. So was that a good enough explanation?
Yeah, it was helpful. Thank you.
So going into BERT, the way BERT works is that it's a special type of neural network that's designed specifically for translating a sequence. And in this case, we decided to translate a sequence of text. When I say translate, I mean it takes in a string of text, right? The string of words that we want to use, and it outputs a series of vectors. And vectors are just like, again, these lists of numbers, and each vector is supposed to have a meaning of a word in a sentence. What makes BERT so special and differentiates it from a typical embedding algorithm is that it actually captures the contextual meaning of a word in a sentence. So here I gave an example of a matrix of how BERT views, quote unquote, views certain words in a sentence, right? Each vector is slightly different because they have different meanings. And here actually plotting the words in vector space, we see we're actually looking at the word bat here, right? Taking the sentence, the bat is my favorite nocturnal animal. In the other sentence, he hit the ball with the bat. Those are two completely different cases of bats, the word bat. And if you hard code it, the machine might automatically assume that they mean the same thing. But here, this BERT algorithm has been trained to know the difference between those two. And we can see that the dots in vector space are in completely different areas.
That's really interesting. And I suppose it's a great way to, sort of visualize how far apart, as you said, those vectors are. So do you mind going up to the image for a second?
Yeah.
Matrix plot? Yeah. So I'm not sure if you sort of looked into this more, because I know this wasn't sort of like the primary focus of your project, but do you want to talk a bit more about what the matrix plot is like, or sort of what it represents, or how the words are divided up?
Yeah, so each word is a vector of length 768. And since we have 6 words in the sentence, it shows 6 vectors from top to bottom. This is color-coded, so I'm assuming that smaller numbers have a certain kind of color and darker numbers, and larger numbers have a darker color. Right? It's much easier to the eye to see than just a bunch of numbers, and it's kind of hard to get the meaning. But we see here that each vector is different, right? No two vectors here are similar, and that's because that makes sense since each word has a completely different meaning.
Yeah, that makes sense. It's kind of like a 768 dimensional vector.
Yes.
And then you're putting it into 3 space, right? With that 3D plot.
Yeah, this is just a representation
Yeah,
of.
got it.
So, oh yeah, here I actually used a pre-trained BERT algorithm, and I leveraged it through a method called transfer learning, which is essentially when I take the data from another neural network and I use it for this one, use it to solve the problems that I'm attempting to solve. And it's a great way to shorten training time. And I also used a slightly different version of BERT called Distill BERT. The reason I did this is because it actually optimizes efficiency in runtime efficiency by decreasing the number of connections there are. But the problem with decreasing the connections is that even though speed is very important when dealing with these extensive neural networks, because the practical applications are severely limited if it takes too long to run, the risk involved with lessening the complexity of the neural network is decreasing its accuracy is that it can decrease its accuracy on new data since it can't extrapolate as well because it becomes less complex. But at the end of the day, given the processing power I had available to me, I thought this was is a really good compromise. So the way this network works is that it's a multi-layered neural network that incorporates BERT at the beginning to capture the context of all the words in the input sequence. And the center embedding is passed through a short, fully connected neural network to output a probability vector. And this probability vector represents the network's guess on what kind of punctuation is associated with a particular word. And because the algorithm predicts punctuation for one word at a time, you actually have to slide the algorithm over the input for all words in a sequence. And yeah, here's the way I made it. Essentially, you have the BERT encoder. You specifically focus on the middle embedding, go through 3 fully connected linear layers, and output its prediction for punctuation. Or if it's no punctuation, to space.
So does
Okay.
it go ahead.
Okay, sorry. So you said it only like finds punctuation for a single word at a time.
Yeah.
So if you slide it through like the words in the sentence, does it also consider context, even though it's only looking at one word, or does like it vary context as it looks at different words?
Yeah, so here the text sequence length is fixed into 21 words. So it gives its prediction on the middle word, but also looks at the previous 10 words and the 10 words after it. And So it still takes context, but uses that context to give a single prediction for that center word.
Got it. And after the linear layer, so it's outputting a 3D vector with like the probability of a period and then the comma and then the space.
So after the linear layer, it just gives out a simple 3D probability vector. It's three-dimensional, so
Yeah, because 3D values.
yeah.
And then you just pick the highest probability, and that's the punctuation after it.
Yes, that is once you go to the post-processing phase, that is how that works. But actually, before that, I wanted to talk about the data pre-processing, because getting the right architecture of the neural network was just half the solution. It's like, what good is a student without any data to teach it with? That's the case with this algorithm. If you don't have data, it won't run properly. And that's where the data selection and pre-processing steps come in. So, like as I said before, for this project, I used A New Kind of Science, which was written by Stephen Wolfram, as it was one of the more modern books in the Wolfram repository that followed generally accepted punctuation rules. But in retrospect, I probably should have spent the time to explore alternatives to this text, since this book featured extensive segments of mathematical equations in code, which isn't precisely quote unquote standard punctuation that most people use in their day-to-day lives. And of course, to avoid dilution of the data and for the sake of simplicity, I focus solely on commas and full stop punctuations, like question marks, periods, semicolons, exclamation marks. And I also had to balance out the data set because I quickly realized the model could achieve extremely high accuracy by simply guessing that there's no punctuation in a sentence. And while that may be right, you'll get like a 97% accuracy if you assume a text only has spaces. What's the point of a punctuation restorer if it doesn't restore any punctuation? So I made sure there's an equal amount of words with different types of punctuation for the training data. Yeah, so the data pre-processing was not perfect here. It's actually one of the more challenging parts. To ensure that the network didn't overfit, I split the database into training data and testing data. Overfitting is something that occurs when the network performs so well on the training data that it can't make extrapolations that is never encountered before. It's like as if you have a student who spends so much time memorizing his study guide for a history test, but when he encountered a problem on the test with slightly different wording, he's taken completely off guard because he was prepared for that study guide rather than the test. So I did train this network on GPU. One of my friends on camp actually offered to train it. Originally, I was trying to train it on my laptop, which does not have GPU training enabled, which is kind of unfortunate. And I was like spending essentially entire days where my model was being trained, and I actually had to a couple of times miss a few hours of camp because my laptop was overheating. But one of my friends, he had a really powerful RTX 3060 Ti GPU. And that was really nice because the training time shortened from 20 hours to 2 hours.
Yeah, I remember from my project at camp, it was very intensive. So I had to like get my dad's computer and run parallel processing on it to try to get all the numbers to work. But I'm glad you were able to get it trained quickly.
Yeah, it's definitely frustrating having my laptop just freeze or overheat. So stepping back a bit, talking about the purpose of this project, the idea behind this is that it's supposed to fix up long pieces of transcription that have been stripped of the punctuation during the data collection process. So if you were to take an audio transcriber, sometimes punctuation isn't there by default. It only detects the words in a sentence. So this is where a punctuation restorer would be useful. And I could also find it useful in personal use. Maybe if you were to take a non-native English speaker, like my parents especially, I can imagine them using something like this to support them in their writing, because sometimes English punctuation can get kind of confusing. It confuses me sometimes too. Like looking at these examples, I wasn't 100% sure what was the supposed correct answer until I checked back in the textbook, the original source. But here are some different examples of how it performed. So we have this input taken directly from the Wolfram book, and then this is the expected output, and it does do pretty well. In fact, we can actually try this out ourselves. Taking this input string. So if I say, so all the punctuation automatically gets deleted. Hello there, Sam, how are you doing? Can you see my text that I'm adding, by the way?
Yeah.
Yeah.
Yeah. Thanks for taking the time to interview me. And you can kind of guess what punctuation is supposed to be there. It'll take a few seconds. So yeah, obviously
That's pretty cool, actually.
yeah.
And it doesn't take too long to make a prediction. It's like a couple of seconds.
Yeah.
Are you using a GPU right now, or are you on a CPU?
No, this is a CPU I'm using.
Wow, that's really cool. Well, that gives me a sort of idea for the future plans, but move ahead.
Yeah, and actually, this kind of gives you an idea of how long it would have taken to train. I don't remember the exact size of the data set, but it was, I want to say around 10,000 sets of 21 word sequences. And if it takes like 7 seconds just analyzing the one sequence, you could kind of get an idea of how it works when it works through that many and it loops through it multiple times. And
And actually, now that we're sort of near the conclusion, I just wanted to ask, have you tried deploying this somewhere? Or because I know Wolfram it also makes it really easy to deploy stuff online. And given that it doesn't seem to be taking too long to do the actual probability calculation and then you're generating sentence, I feel like this could be a good candidate for deployment.
yeah, it's something I was considering. I think there are a few things I want to fine tune though before I actually implement this. The two things being, I want to train it on more data because Stephen writes in a very specific style, right? Everyone writes in their own unique style. So punctuation slightly differs in different texts, which is why by making the model train on a larger variety of text, it's probably going to be able to perform better on real world data that it hasn't looked up before. So yes, I go ahead.
So I guess you mentioned that you wanted to go ahead and train it on like a different type of training data other than just Stephen Wolfram's book. But beyond that, is there like any application of this that you see being used somewhere, or like what do you want to do with it now that you've finished this stage of the project?
Oh yeah, definitely. Once I'm able to like get this working properly so that it can be used in real world scenarios, I think it would be really useful for because there's a huge portion of text databases that are just completely unpunctuated, and it's like a vast source of information that other machine learning data scientists, AI people, AI engineers can't use properly for the text purposes. So having a strong punctuation restorer with high accuracy is very essential for these purposes, so they can tap into this vast field of unpunctuated text. And this is like with a closed captioning tool or and OCR being used to convert physical documents into virtual ones. They aren't always perfect. I think I've used some myself before, and I've seen how they can mess up just entire pieces of text, and you realize, oh wow, this is not punctuated properly at all.
Yeah, that sounds pretty cool. Cool. So I guess after doing your entire project, what would you say was your like most favorite part out of everything you did?
My favorite part of camp or my favorite part of the project?
Yeah, the
Either, I
favorite part.
suppose.
Either's fine. Yeah.
Yeah. But
I,
perhaps if you have something that stands out about the project or something you would like to mention there.
I think I'll say both because my favorite part of the camp was probably the morning activities and just being able to connect with my campmates. That was always nice and exciting. And also my mentor, Kurt. Hey Kurt, if you're watching this, he was he was really nice to me, and I really appreciate everything he did for us, for me and our group. And then there's also the project. I think for me, my favorite part was like the satisfaction of seeing it actually the model working on not only the training data but the testing data. That that was like a big step for me. So the first time I did it, I realized there's something wrong with my data pre-processing. It was just really nice to see because there's also the question that actually Stephen Wolfram told me. He brought this into question saying, can you use machine learning to solve that problem? Because there's a potential that on my project would be about saying that you can't use ML to do this because it's not perfect neural networks. But I was able to figure out that you can use uh, pure deep learning to solve this problem of just putting punctuation back into a piece of text.
That makes sense. And I guess talking about the camp, I mean, yeah, I really agree. The morning activities were definitely a very, very interesting part of the day. So, and we also had like evening activities sometimes, or evening for them. That was like late night for me in India. But yeah, it was a fun time. And given your project, you have so much going on. It's really detailed and a lot of parts, I'm sure, were really complicated to understand and code, just because of how much sort of depth they need, depth of knowledge. Were there any parts that were especially challenging for you, in terms of, perhaps understanding the concepts or implementation or anything like that?
Yeah, for me, the hardest part by far was the data pre-processing. I've made a few neural networks before, and I knew it would be difficult, but I don't know, dealing with strings can be annoying. The Wolfram language, Mathematica, its modules made it, its functions made it much easier. Just again another really good learning experience for me to see how to manipulate text to in a way that the model could input it. But just figuring all that out was was difficult. It was really difficult to pull off.
I'm glad you had a wonderful experience using the Wolfram language. So yeah, once again, thank you so much for joining us, and thanks a lot for sharing your project. And I wish you best of luck on taking this project into the future as well as all your other endeavors.
Of course, thank you. I really appreciate this nice conversation. So,
Same here.
Yeah, thank you and good luck in everything you do.
yep. Bye.
Bye. Have a great day. Thanks for listening to this episode of the Wolfram Student Podcast. We hope you learned something new and took away insights from today's discussion. If you want to be featured in a future episode, fill out the form at tinyurl.com/wsp-interest-form.
And be sure to tune in 2 weeks' time to hear our next episode. Once again, thanks for listening.
Bye.